So first of all, thanks so much for all the speakers that spoke in the morning session. I know for me personally, especially the set of speakers is always really exciting and kind of inspirational to see all the work that's being done in this general field of miniature microscope development and development on analysis, and really pushing this type of work forward, which is really exciting. So we've gone through yesterday talking about how to, the principles behind miniature microscopes, things to think about and consider when thinking about the experiment you want to do. Went through how do you actually do the surgeries? How do you get optical access to cells you're interested in and brain regions you're interested in looking at? Then how do you go from an assembly kit that you might try to source all yourself or purchase from an open source distribution company? How do you go from that pack of individual components to a functioning miniature microscope? And then how do you use that on a freely behaving animal, make sense of the behavior, and acquire and save behavior and neural data? And then again, this morning we saw all these amazing talks. And so now we get to what I think will be one of the most useful sessions here, which is to talk about how do you start processing this raw imaging data that comes out of a miniature microscope. So leading this talk is Phil Dung, who's a graduate student in Denise Cai's lab, and I've had the pleasure of co-mentoring him on some projects. He's really spearheaded this pipeline that he's going to be talking about today called Minion, which really tries to incorporate all of these great developments that have happened over the last few years in pushing forward these pipelines to process single photon neural imaging data, and then potentially kind of open up the box so they feel less intimidating when you have to deal with adjusting individual parameters that maybe you don't know exactly what they're doing. And how do you sort of like validate the output of these systems? So the idea here is really to make a pipeline that's understandable for the vast majority of neuroscientists. I mentioned this also before, that it really ends up being the case for most labs starting to use miniature microscopes, that like the large hurdle isn't building the miniature microscope, it isn't doing the surgeries or doing your behavior. The hurdle almost all labs run into is then how do you process this data? Oftentimes it's labs that have gone from not doing any of this kind of single cell imaging, but doing, EFIS, where your output is already the nice time traces from your cells for the most part, or fibrophotometry, where you just get one or a couple of time traces from the neural population you're looking at. Neural imaging with single cell resolution is a bit different because there's all these processing steps that you need to take before you get to an output that you can start doing science with. And there's a lot of places, you have to do a lot of critical things, and they're all very powerful tools, but there's also a bunch of places that can cause issues. And so Phil will walk us through his work on the Minion pipeline, as well as just the general approach, I think, to doing kind of all these processing steps to go from raw neural imaging to traces of activity that you can start coupling with behavior. So with that, I think, Phil, you can share your screen. Again, I'll mention, if you have questions, you can type them during his talk in the chat window. We'll try to answer those along the way, and then there should be time after his talk for some kind of other questions for the last 10 minutes or so.
Awesome. Thank you, Daniel, for the introduction. Let me try to share my screen. So can you see the screen, the slides? Okay, perfect. Okay, so hey everyone, as Daniel mentioned, my name is Phil Dong. I'm a graduate student from Denise Lab. And today I'm gonna share with you this Miniscope analysis pipeline called Minion that we have been working on for the past few years. So as Daniel mentioned, you have been hearing about how to do the surgery, how to do the behavior, how to do the recording. And after that, you get some sort of data that looks like this. And then you face a problem that is, how do you extract neural activities that's suitable for downstream analysis from this raw video? There are quite a few factors that can make this problem particularly hard. There is the motion of the brain. There is autofocus scattering. There are noise from the sensor. And lastly, if you're imaging a dense area like CA1, you have a lot of cells overlapping with each other. And all of them have to be dealt with in order to get the correct trace out of the video. Luckily, there are already a lot of great pipeline and algorithms out there to deal with these problems. So for example, non-REM core not only correct for the translational motion of the brain, but also the non-rigid motion of the brain. MiniPipe has a really good way to handle the autofocus scattering in a really efficient way. Of course, the CMF algorithm is sort of the gold standard in the field to extract cell activities. It's specifically designed to handle overlapping cells and to mix their activities. And lastly, we have Caiman, which you heard from Andrea, and it's a Python package that's kind of put together a lot of algorithm together into a kind of one-stop Python analysis pipeline for calcium imaging. So all of these pipelines are great, and they'll give you like a great result as long as you can choose the proper parameters, as long as you can use them kind of properly. But actually in practice, as Daniel mentioned, we face sort of a new problem, and that is for a lot of us who doesn't have a strong computational background. These pipelines sometimes function like a black box. So you feed in your data, you let it run on the data, and then you get the traces out of it. It's really hard for us to get to know what's exactly going on behind the scene and sort of control how my data is being analyzed. If you really want to dive into that, you need to dive into the math, which have a lot of parameters. And then if you really want to take control, you need to figure out how this mathematical equation actually implemented in the code, which usually means you need to go through pages of source code, and it'll be hard to go to kind of know all of them and be on top of it. So in other words, this creates gaps for neuroscientists to really take control of our data analysis. And to solve this sort of new problem, we developed a Minion. So here is an overview of the pipeline of Minion. As Andrea mentioned, this calcium imaging analysis pipeline are quite similar to each other. We have kind of stereotypical different steps. The first thing we do is do pre-processing, and then we motion correct the movie, and then we use the CMF algorithm to iteratively update the spatial location of cells and the temporal activity of cells. So as you can imagine, Minion is not coming out of nowhere. It's heavily inspired by the existing works out there in the field, especially Caiman and MiniPipe, where I basically take a lot of inspiration from, and I sort of copy a lot of algorithm and logics in these existing pipelines. But what's special about Minion is that we try to improve the transparency and accessibility of the algorithm. We do that by providing interactive and user-friendly visualization for every single step in the analysis. We try to reduce the memory demand as much as possible, so you can run longer recordings on even something like a laptop. And lastly, we try my best to provide as much documentation as possible, so people really understand what each step is doing. So here is a quick look of the interface of Minion, which is basically a Jupyter notebook. We choose this interface because you can run the code, see all the comments and tips, and actually see the result and visualization here, all in one interface. So we believe this makes it much easier for scientists to absorb and see how the algorithm is doing. Here is a quick a result from a benchmark we did. So here we run Minion and Caiman together with a bunch of simulated data, and we show the computational demand of the pipeline. You can see that for the runtime or processing time, both pipeline have quite similar performance, and they sort of scale linearly with the size of input data, which is shown as a frame number here. But when you go to peak memory usage or memory demand, you see that Minion really try to maintain a constant memory demand regardless of recording length. While for a lot of pipeline in Cayman, in this case particular, you expect the memory demand to sort of scales linearly with the data size. So with this, we really improve the accessibility of the algorithm, so scientists can run stuff without specialized hardware. So with all that, I hope you are as excited about Minion as me, and I would like you to walk you through a few critical steps in Minion, basically walk you over the pipeline, so we have some basic understanding of how usually you deal with the imaging data and extract neural activity out of it. So we're gonna start at the very first step, which is the pre-processing of the data. So the goal of pre-processing is mainly twofold for Minion. We want to remove some sort of noise and artifact from the video so that it's clean and ready to be processed further. In particular, we want to remove the autofocus fluorescence from cells that's not really in the field of view. And secondly, we want to remove this salt and grainy type of noise that's usually result from imaging sensor, and that's the two main goal of the pre-processing step. And before I go into talking about how exactly we do this, I want to sort of introduce a basic concept for image processing, just so that everyone is on the same page, and that is something called a kernel. So a kernel is a way we represent how we compute the pixel value for image processing process. So the way it works is that for each pixel in the picture, you put that in the center of this matrix here, and then all the numbers surrounding that tells you how much weight the surrounding pixel is going to contribute to the new value of the center pixel here. So for example, here I'm showing like a 3x3 identity kernel. It's basically not doing anything at all because the weight of the center pixel is 1, and all the surrounding pixel doesn't contribute anything to the new value. So the result of this is basically you get the same picture in return. It's not really doing anything. Here is an example 3x3 mean filter kernel. The effect of this is that for each pixel, you take the mean value of this 3x3 window of the surrounding pixels, because all of these number are 1 here and all the pixels contribute equally in this kernel. And the visual effect of this is that you have a blurred image because, for each pixel, you're kind of averaging across its neighbor. Here is an example of a 3x3 Gaussian kernel. It's sort of similar to the mean filter. The only difference is that the weight distribution follows a Gaussian curve, and you have a slightly more emphasis on the center pixel. And the effect is also blurring, but maybe slightly more centered towards the original pixel value. So other than different types of filtering and kernel, you can also have different size of kernel, and they're also going to have different effect in image processing. So here's an example. We have a 3x3 Gaussian filter, as you just saw in the last slide, and on the right. Sorry, can people hear me again? Sorry, my headphone is going crazy. On the right side, we have a 5x5 Gaussian kernel. And you can see that, as you can imagine, when the kernel size is larger, the effect is that your images are basically more blurred. And so this is just showing you that in addition to different kernel, you can have different size of kernel, and they will produce different effect. So with that, we're ready to dive into how Minion do its job at pre-processing. The very first step we want to do is we want to get rid of the sensor noise. And the way we do that is we use a median filter. So here is the effect of a median filter. Before the filter, you see this little pixel length value that's mainly resulting from sensor. And after the median filter, you see they are mostly gone. And then we use the median filter to do this. And the idea is basically that we take the kernel, and instead of doing an average or anything, we take the median value within a kernel, and we use that to sort out to filter out the grainy noise. And this type of filter is specifically strong against reducing this salt and pepper type of noise. As you can imagine, the size of the kernel is one critical parameter for this step to work properly. And here is a Minion visualization that can help you determine what's the best kernel size you should use for this. So on the left, we have the image before and after the median filter. In the middle here, we have the corresponding contour plot of these two images before and after the filter, where basically the pixel that's of the same value will be plotted as the same contour in this plot. You can see that when you use a kernel size that's too small, the median filter is not really doing much, and you can see clearly in the contour plot that even after the filtering, you have a lot of these tiny little islands left here, which represent the sort of grainy noise in a sensor. And if I try to play this video, so here's a better view when you zoom in. And you can see that when you start to increase the kernel size, these sort of islands are more left out, and then they're better filtered. But when you use a kernel size that's too large, like something like here, the image become too blurry. And you start to see like even these two cells here, they are starting to connect to each other. And you don't really want this to happen. So in this particular case, we want to avoid both too small and too large, and we want to choose something in the middle as our proper kernel size. So that's the denoising step. And after that, we're ready to remove background fluorescence. So here is the goal of background removal. You see that before the background removal, you have a lot of out of focus fluorescence in the background here. But after that, image is really cleaned, and you see the contrast of cells are sort of improved. So we use something called a morphological operation for this step. And here is some animation showing what it is doing. So the morphological operation is composed of two fundamental operations called a erosion and a dilation. And the idea is sort of similar. We have a kernel that's kind of moving around the image, but instead of median or average, for erosion, we take the minimum value within the kernel. And on the contrary, for dilation, we take the maximum value within the kernel and use that as the new value of the pixel. So as you can see with these two animation here, the effect of erosion is basically it sort of erode away any bright blob that's smaller than the kernel size, because as the kernel goes through here, it's going to take these dark pixels from the neighborhood and use that as the new pixel value. So the effect of it is it takes away any bright feature that's smaller than the kernel. On the contrary, the dilation do sort of the reverse. You kind of expand the bright pixels by the size of the kernel. So as you can see, when it moves to this little bright circle here, it kind of expand everything to the neighboring pixel. And with these two fundamental operations in mind, we can go about and remove the background. And here's how we do it. We take a single frame, a single image, we apply the erosion to that. And as long as we choose a kernel size that's just slightly larger than the cell, we'll see that anything that's smaller than the kernel, which are basically all our cells, will be eaten away. You will see this kind of dark holes in the image because the bright cells are eroded away. And then we take this image and we pass a dilation process to it. And the effect of that is, it takes the pixels that's immediately surrounding the holes and it sort of fill in the holes with a brighter pixel value. And this image right here is essentially our estimation of the background. And after that, all we need to do is to subtract this from the original image, and we get sort of like a clean image of cells without the local backgrounds. So again, as you can imagine, the kernel size of this morphological operation is again a critical parameter for it to work. And in Minian, we use basically the same visualization to help you determine what's a proper kernel size for this step. Again, we have the image before and after the background removal plotted here. The corresponding contour is plotted in the middle. And you can see that when we use a kernel size that's too small, you sort of artificially reduce the size of cells because it basically functions as a size filter. So if I try to play this, you can see that when you zoom in, the size of these cells is reduced by some sort of amount, which is not a true reflection of what's going on. On the other hand, when you use a kernel size that's too large, you can see that it left out a lot of local backgrounds even after this step, which is not what you want, because the goal of this step is to remove background. So again, we want to avoid both extreme cases, and we want to use a window size that's in between. And this visualization help you to do that. Okay, so with that, we are done with pre-processing. We'll have a movie that's kind of clean of noise and background. The next thing we want to do is we want to do motion correction on it. And the way we do motion correction is quite similar to our pipelines. You probably heard this in the morning already. Here's a basic idea. You have an image, and you have in theory you have a slightly offset image, and the way we correct for that is compute a cross correlation between these two. Here is a cross correlation plot on the right side. Basically, each pixel here represents a particular XY shift, and the color represents the correlation value. And the way we find the optimal shift is where we look at the XY shift that corresponds to the maximum correlation value between these two images. And this is how we correct for motion for any pair of frames, basically to do this to consecutive frames over time. So that's quite a simple. And after motion correction, we end up with a movie that's kind of clean of everything and also motion corrected. We're really ready to extract cells from this movie. So basically the bottom row here in the pipeline is all about extracting cells with the CMF algorithm. And here is a quick refresher for the formulation of CMF. Again, you have heard of this in the morning already. I'll try to be quick. So we assign the letter Y to represent the raw movie, which is basically a 2D matrix of the raw movie, and each row here represent a single pixel in the movie. We assign the letter A to represent the spatial footprint of cells, where each column here is the spatial footprint of a single cell. And we assign the letter C to represent the calcium activity of cells, where each row represent a single cell. And then the CMF formulation basically say that the input movie can be broken down into the product of the A matrix and the C matrix, plus the background term and the noise term, right? So this is basically the most important thing to understand about CMF formulation. On top of this, CMF algorithm assume certain temporal waveform of the calcium activity. In particular, it assume an autoregressive model to model how calcium events arise from spike signals. So basically, the goal of CMF algorithm is to extract this A and C matrix from the raw input data and to decompose the signal so that you get some estimation of the underlying specs. Okay, so sounds like this is good, and sounds like CMF algorithm is all we need to do next. But just like any other optimization algorithm, in order for CMF to work, we need an initial guess of the two matrices A and C here, because what CMF can do is to refine this for you, but it cannot sort of generate this out of nowhere. So that's why we need to do another step right before the CMF updates, and that's called seeds initialization. The goal of this is to initialize initial value for the A and C matrix, and we do this with something called seeds, which are basically like single pixel value that that's representing the putative location of cells. The first step we do in the initialization is we generate an over complete set of seeds, which are represented by this white dot here in this plot. So the way we do this is quite straightforward. We take local maxima on a max projection of the movie, and this local maxima will become our potential seeds. In order to capture all the activity and in order to avoid dimmer cells being overshadowed by brighter cells nearby, we not only do this once, but we compute max projection on different subset of frames and do this over and over again and take the union of all the seeds we get to have an over complete set of seeds to begin with. So that's the first step. That's how we sort of generate a guess of the location of cells out of nowhere. Then we want to sort of refine these seeds a little bit, because the seeds are kind of overcomplete. There will be a lot of false positive in there. And one thing we can do is we do something called a peak to noise ratio refine. So the idea is this: for any temporal signal of a seed, you can filter the temporal activity and break it down into a high frequency component and a low frequency component. And because the calcium activity are expected to be relatively slow compared to noise, you expect the calcium signal falls down into the low frequency component when you do this. So as you can see here, here's an example of a real cell and whose temporal activity is broken down into these two component based on frequency. And you can see a clear calcium event in this red signal low frequency trace. And on the other hand, the noise trace kind of doesn't contain anything real. If you look at a false positive seed, you see that the low frequency component doesn't really contain any significant fluctuation. And the amplitude of this signal is sort of comparable to the noise trace. So with this idea behind, we define the peak value as the amplitude of fluctuation of a low frequency component. And we define the noise value to be the range or the amplitude of fluctuation of the high frequency component. And the way we filter our seeds is basically compute the ratio between these two values. And we say any seeds that have a relatively low peak to noise ratio is probably not real. It's probably a false positive. So that's the idea behind this peak to noise ratio refine step. As you can imagine, in order for this step to work properly, it's really critical to define the correct cutoff frequency to separate the low frequency and high frequency component. And here is a Minian visualization that help you determine what's a proper value or proper cutoff frequency to set. So we have the temporal activity of 6 randomly selected seeds plotted here. They are all broken down into the high frequency and low frequency component. We're gonna just call them signal and noise for now. And as you can see that when we choose a cutoff frequency that's too tiny, what's going on is that every single fluctuation is basically in the high frequency component, the blue trace here. So let me play the video here. And you don't want that because that's not noise. That contains real calcium activity. But then when you start to increase the cutoff frequency, you see the signal and noise start to separate from each other. But then if you keep increasing further and choose a cutoff frequency that's too high, you see that these high frequency fluctuations start to bleed into the red trace again. So again, this is not a good estimation of signal versus noise. So we want to avoid both too low and too high again. I want to choose some value in between. And this visualization help you to choose a proper cutoff frequency, which is not only used for this refined step, but it's also critical for a lot of other steps down later in the pipeline. So with that, once we are satisfied with our choice of seeds, when we generate them and we refine them, once we are happy with that, we go ahead and try to generate initial A and C matrix from these seeds. So the way we do that is sort of straightforward. For A, we take each seed and we compute the correlation of each pixel relative to its neighbor. And the correlation value itself will be our initial guess of the spatial footprint for each putative cell. For the temporal activity of each cell, we basically take the spatial footprint and we use that to compute a weighted average of the temporal, the raw fluorescence value of those pixels, basically. And that will be our initial guess of the temporal activity. We also generate initial background terms, the B and F here, by basically subtracting the cellular activity estimated by A and C, and sort of take the spatial and temporal average from the raw movie and use that as our initial guess on B and F. If you remember Andrea's talk, this is a very sort of crude estimation of complicated background. The reason we choose to use this single rank term as background is that we adopt the background removal step from Minipep, and we already did that in the pre-processing using the morphological operations. I'm sorry, my headphone keeps turning off. I'll try to talk faster. So the reason we do that is we already sort of get rid of the background. And in practice, we see that using a single rank term is good enough for our purpose for extracting cells. So with these initial 4 terms, we're ready to go into the CMAF algorithm, which composes of an iterative update of spatial footprint and temporal activities. So the first thing we do is usually we want to run a spatial update pass first. And the goal of spatial update is basically given an initial guess of the spatial footprint, we want to refine them further based on the model and get a better estimation of the location and the shape of cells. And the way we do that is defined by this optimization equation. I'm not going to go into the details of the math here, but basically conceptually what this equation is saying is that for a given pixel, you want to find the corresponding trace of that pixel, and you want to find a weight for each unit such that the temporal activity of the units best fit the temporal activity of this particular pixel. But at the same time, you don't want to go too crazy and kind of put a weight on every single unit, because that will give you a non-sparse result and making the output really hard to interpret. So as you can see that this equation sort of have 2 competing goals. On the one hand, you want to fit the data as much as possible. On the other hand, you don't want to overfit so that it kind of give you a lot of small values over the place. So there's a single scalar called sparse penalty that's controlling the balance between these 2 goals. And as you can imagine, setting a proper value of sparse penalty is really critical to carry out the spatial update properly. And here is a Minian visualization that help you determine the proper value for sparse penalty. Here's we have 10 randomly selected unit. and we plot their spatial footprint here on the bottom left. At the same time, we plot the bannerized version of the spatial footprint here on the top left. The reason we do that is the user can easily see all the non-zero values in the spatial footprint, which will help inform you like whether the sparse penalty is proper. We also have the temporal activity of these 10 cells plotted here on the right, just for reference. And you can see that when we have a sparse penalty that's too low, the model tend to overfit the data. And what's going on is that the spatial footprint of cells sort of extend to neighboring pixels and give you a really kind of unnatural shape, which is sort of evident here in this bannerized version of the spatial matrix. So let's play this video. We can see these different cells, and we see that with low sparse penalty, the spatial footprint are really large. But when you increase the sparse penalty too much, you see that it's really starting to constrain how much you can put in the spatial footprint, and it makes everything tiny. In this particular extreme case, it even drops cells for you, which they looks like they have real calcium activity, and you really don't want that to happen. So again, we want to avoid both extreme case and use a sparse penalty somewhere in the middle, and Minion help you choose this value using this visualization. So with that, we're ready to go to the temporal update. We usually do this iteratively, do one after another. And then the goal of temporal update is sort of similar. You have an existing estimation of the activity of cells, and you want to update that so that the model can fit the specs and calcium activity for you. And at the same time, you want to deconvolve these traces so that you have an estimation of spec. And the way we do that is again defined by this equation. And we sort of do the two goal at the same time with this equation. So conceptually, what this is saying is that for a given set of unit and their temporal activities, we first want to determine the relationship between the calcium traces and the spikes. We basically want to estimate the parameter for the model. And then we want to estimate the calcium activity and the specs that best fit the data to, basically minimizing the error. But at the same time, we don't want to go too crazy and let the model put a little spec on all the frames in your recordings. That will make the result really hard to interpret. So again, it's quite similar to spatial update. You have two competing goals in this single optimizing problem. You want to fit the traces, but you don't want to overfit them so that you end up with a lot of noisy specs. And again, a parameter called sparse penalty is controlling the balance of these two goals. And here is a visualization that help you to determine the proper value of this. So we have the temporal activities of a single neuron plotted here. The raw noisy signal is plotted in red. The fitted spikes signal is plotted in green. So you see these little tiny spikes. The fitted calcium is plotted in like orange or blue. They're usually overlapping with each other. And in addition to this, we also have the calcium waveform of a single calcium event plotted here for your reference, and then the spatial footprint of this cell here for your reference. So you can see that, well, first of all, you can scroll through different cells and to get a feeling of what's going on in general. But you can see that when the sparse penalty is too low, you have a lot of this noisy spec. But when you start to increase that, the model estimated specs start to decrease and go away. But if you go too much, and in this extreme case, you see that it's starting to miss real calcium activities. And again, you don't want that to happen. So again, this visualization help you to determine a good value for sparse penalty. And you want to use something in between that's not too low, not too high. And that will give you a good result and good estimation of calcium and specs. So that's basically sort of the end of the pipeline. We usually do multiple iteration of the CMF update. We found that in practice, usually 2 is good enough. And after all of this, here is what you can get from Minion. By default, Minion will give you a video where we plot the raw input data on the top left. We have the pre-processed and motion corrected movie on the top right. We have basically the CMF output or the modeled cellular activity plotted on the bottom right. We have the residue here on the bottom left. So you can see that, if everything is working properly, most of the cellular activity are captured by the model, and the background and noise are left at the bottom left here. So, that's sort of the goal of the whole pipeline, is to give you a result like this. And then after that, hopefully everything is easy and you get to analyze your own data. And then this is sort of the final goal, with other open source tools like EasyTrack that you already heard of. You can easily carry out place cell analysis like this, or even much more fancier downstream analysis. Minion is available on GitHub, of course, and I'd love everyone to give it a try. And hopefully you'll enjoy that. And with that, I would like to acknowledge all our funding sources and thank my fantastic PI and all the lab members without whom Minion will not exist. And I would also like to thank all our collaborators, Daniel, Tristan, and Kanaka. And thank you for your attention.
Awesome. Thanks so much, Phil. We have some time if people want to raise their hands and ask questions or type them into the chat. There's already some questions. One that came up a little bit earlier is how would you expect Minion to perform on 2-photon data? Is something you guys have tried before, and if not, do you think it's something that would work?
Okay, so personally, I haven't tried to actually run Minion on 2-photon dataset, but I would say that, as I mentioned, Minion is really built on top of the existing pipeline. The core CMF algorithm should be identical to what's out there, like Kaiman. So in that sense, Minion should, in theory, work on 2-photon data as well. The only thing I'm not quite sure is it's the thing that's different. So for example, in the pre-processing step, we use a morphological operation to select cells that's kind of assuming a round shape, like a blob. I'm not sure how well that will work on 2-photon. Also, the seeds initialization, we have yet to test how well that will work on 2-photon data. But other than that, I would say everything else is quite similar, and with some tweaking, it should work on 2-photon data as well.
Cool. There's another question, which is, I think it's come up a few times in the chat, which is so once you kind of dial in parameters, do you expect that, do you need to kind of figure out what the parameters are on a per recording session basis, or can you dial them in across, across all recordings from the same animal, or can you, within a whole experiment, be able to figure out parameters that could be applied across all animals in that experiment?
Yes, that's a good question. So usually what we do in lab is that we do some visualization for 1 or 2 sessions from the same animal, and usually the parameters are almost identical with the animal. So as long as nothing crazy is happening, we try to make sure all the parameters are the same for a single animal at least. Then for a certain experiment where the scope you're using the same, the brain region you're imaging the same, we try to use the same parameter, but at least we'll sort of make sure all the parameters are working on each animal's basis. So for each animal, we take 1 session, we see, we visualize everything, we make sure all the parameters work. If they don't, I'll go ahead and change them based on animal. One thing I think that could potentially be really different is the density of cells, which for sure will affect a few parameters in the pipeline. But usually they are quite, the difference in parameter are quite minimal within experiment. So yeah, so the approach we take is usually, make sure same animal use same parameter and try to keep it consistent as much as possible.
Cool. Jason had a question in the chat, which is, what is the kind of data output of Minion?
Oh, that's kind of an interesting question. For whatever reason, I choose to use a not very popular library called X-array. It's kind of like a NumPy array, but on top of that, there's a lot of metadata being saved. So that's the kind of the native output of Minion. But with Python, like a lot of open source library, you can easily convert between them. So X-array can be directly saved into a format called netcdf. I think MATLAB is something people use, and even MATLAB can read it in. If you don't want the metadata, you can easily get the NumPy array out of Minion, and you can easily export that to all kind of formats. And I'm sure there will be a way to export it to the format you want.
There's a question earlier on about motion correction, and I think I'm right when I answered it, but the motion correction currently supported in Minion is just kind of a rigid translation motion correction. If someone wanted to incorporate something like normcore that also tries to correct kind of local motion, what would be involved in doing that?
Well, first of all, you're correct in that by default right now, Minion only support rigid translational motion correction. And again, the reason we do that is in practice, at least in our hand, after the rigid motion correction, the video are fairly good enough for downstream processing. But if you want to incorporate non-RIM core, well, I guess you have to sort of rewrite the motion correction function. I did hide a few parameters in the motion correction function. That's sort of trying to do that with an existing library, but that's kind of in practice when I run it, it basically gives me the same result I get from the rigid motion correction. So that's why it's not enabled by default. If you want, you can give that a try. I'd love feedback, or I'd love community contribution to put in non-RIM core in Minion. That would be awesome.
Cool. There's a couple questions about going from this Minion pipeline, which is does kind of a per session analysis. Then what do you do to then track cells across days?
Right. So Minion by default provide a notebook to do this. The algorithm is quite simple. I won't go into detail, but it's based on basically only the location of cells. It's basically saying, if cells are close enough to each other and they are kind of mutually nearest neighbor, they will be kind of consider the same cell. If you want to take this across more than a pair of session, I do this. I do all possible pairwise registration, and I try to sort of resolve any conflict. But my strategy for this is being really conservative. Is whenever there's a conflict happening, I would kind of drop the mapping and say, okay, I don't know what's going on with this cell. I'm not going to say they're the same cell in any of the sessions. So Minion does have that algorithm. It is on the conservative side. So a lot of people sort of tried it and tell me, it's kind of, especially when you have much more sessions, it's tend to give you very low number of cells that's kind of active across a long time. If you want, Minion can easily, again, be exported into a format that MATLAB can read, and then you can use the cell reg algorithm, which is developed by Yaniv's lab, which I heard many great things about it. It has really good modeling of the distribution of this, and you also take the shape of cell into account, and you can give that a try, and everything will be compatible.
Cool. Some people also will attempt to concatenate all their sessions. Like let's say you did like 8 sessions of the same animal, you just put them into one big long data set and then just run it once through one of these pipelines. Do you have any opinions on that approach?
That's sort of our dream because that's one of the motivation we really try to minimize the memory demand. Because you can imagine whenever you do that, the biggest bottleneck is going to be memory because you just can't load that long recording into memory. So our in theory Minion should work with fairly arbitrary length of data. And in theory, you can basically do that like concatenate video, or maybe even just put them into the same folder and rename them so Minion can just read them natively. I have to say, I haven't personally tried it, so I couldn't guarantee anything. I think one of our lab members is about to try that, exactly for the difficulty in registering cells across session. Maybe it's easier to basically just cheat the algorithm and tell it to handle everything as a single recording session. So yeah, it's possible at least, and I'd love to hear if anyone have tried that.
Cool. Andrew has a question about, I think most of the data that's shown throughout the entire workshop is just the standard GCamp 6F or something, or I guess maybe newer versions. But would you expect if you start to use somatically localized GCamps, would it significantly improve the output of these processing pipelines?
Yeah, I mean, that sounds definitely true. Yeah, because especially a lot of this step in the pipeline sort of assuming like a round blob shape of cells. If they're really localized, I assume it will really clean up everything.
There's also the high contrast, the C version of GCamps that are somewhat designed for single photon imaging that also could help.
Yeah, I would love to see those data.
Cool. Okay, we have more questions, so we have a few minutes, so let's just try to hammer these ones out as well. Does this pipeline work well for both version 3 and version 4 Miniscope data? And do you have any advice for dealing with optical artifacts like dark spots from like dust on the image sensor and things like that?
For version 3 and version 4, I don't think there are anything that need to be modified. The only difference is, different side of field of view. I think the cells in version 4 tend to be smaller than version 3. So apparently you want to change some parameters to account for that. That's the only thing I can think of. But that's what the visualization is designed to do. Dark spot. I would say, well, this it's probably very hard to recover the information that's hidden behind the dark spot. So I guess those will just be lost, and Minion certainly.
I think this question was also maybe partly assigned to like when you do motion correction, if you have dark spots that are stable relative to the pixels and grain that moves, how do you deal with that?
Yes. So that's the only thing I can think of to sort of deal with it. It's exactly as Daniel mentioned, it might mess up the motion correction. The way we usually do that is quite easy. Minion has a visualization of the movie. It's kind of like a tiny video player, and in that player you can easily draw like a square mask of a field of view. You can use that mask to tell the motion correction algorithm to only use data from that part of field of view. So as long as you can draw like a mask that's avoiding the dark spot, the stable sort of feature in the field of view, you can tell the motion correction algorithm to essentially ignore the dark spot and use only the moving part to do the correction. So yeah, that's the only sort of practical tip I would say whenever you see a dark spot.
Cool. Okay, we have 2 questions and then we'll move on. So I think this is a really good question from Simon.
Yep.
Is Minion likely to be actively developed over the next few years? Is there a plan to support this sort of long term?
I might allow to, I don't know. Personally, I will try my best. I will do it, on whenever I have time for that. I think we talked about this before, there's potential collaboration with MetaCell, who is hosting us here today. Maybe they can help maintain the package. They already help a lot in putting, making sort of automatic testing, all this stuff to make sure I don't break Minian, whenever I try to do something, they already have been really helpful in this. So maybe MetaCell can help this. You know, the more future long-term plan, probably Denise can answer that better. It's
Yeah,
not
I will
here,
also
so.
say just in general, right, there's this growing understanding in neuroscience labs as well as from funding agencies that this is not an insignificant problem to solve, right? More people are using tools that generate larger and more complex data sets. And so it's this big open challenge of like, how do you really solve these issues so that any lab can actually use these novel tools and make sense of them. So while it maybe in the past has been more difficult to get external funding to kind of continue and support the development, Hyman is a really good example of like ongoing support and continued maintenance of the package. And I think that will grow more and more across time, right? So I think the simple answer is it's hard to maintain a package. Phil does a really great job at doing that. And hopefully the MetaCell, of course, is also committed to trying to kind of support this avenue going forward. And I think there's a bunch of solutions for long-term maintenance in the future.
Yeah.
Okay, last question in 1 minute. What is the max length recording video that Minion can currently handle?
Oh, I would love help from the answer. As you can imagine, I don't really personally run a lot of experiments. So, all the information I hear is from my lab mates. I heard maximum 2 hours maybe, but if anyone here has a say on that, like longer than that,
Theoretically, it should go longer. And
theoretically, it could go arbitrarily long. Yeah.
We have some 24-hour recording data sets that we are trying to get fully up and running, and we've run into some kind of strange issues along the way with Minion as you start going to these very large data sets. But theoretically, it should be okay for long data sets, right?
Yeah.
Okay, cool. So if there's other questions that we weren't able to get to now, you can, while we don't have a breakout room for all the participants after this session as we did yesterday, you can go to the GitHub site of Minion and post a question or an issue right on GitHub. You can also go to the Miniscope Google group and ask questions about Minion. And then there might be some in the future Slack channel where people can discuss these types of issues of kind of how do you handle processing neural imaging data. So great, thanks so much, Phil, and thanks everyone for the great questions.